topic we'll discuss today is infrared spectroscopy. Just like mass spectrometry is carried out with mass spectrometer, infrared spectroscopy is carried out by the infrared spectrophotometer. So we have in mass spectrometry, which is a method for determining the molar mass of molecule as well as the percent abundance of isotope, we will be using the mass spectrometer. So this method allows the determination of the percent abundance of isotope when we are using mass spectrometer to analyze element. Okay, so percent abundance of isotopes. And when we use mass spectrometer to analyze compounds, we can study the molar mass and structure of compounds. Okay, so know the difference between elements like chlorine, bromine, and compounds. Okay, so compounds like the isomer we discussed, propanol and propanone. So of compounds, so e.g. propanol, propanone. So remember the example where we compare the mass spectra of propanol and propanone in order to distinguish between these molecules. And when we use mass spectrometer to analyze elements such as chlorine and bromine, we found that they have different isotopes with different percent abundance. So that's mass spectrometry, okay, measured by mass spectrometer. So in this chapter, we look at infrared spectroscopy, which is studied using another equipment, and that is infrared spectrophotometer. So we learned about the detailed workings of the mass spectrometer, and we learned that it looks kind of like this. Okay, it looks like a bent rod of some sort, and there are many different processes that happens in many different parts, okay, of this equipment. So we have vaporization, we have ionization, we have then acceleration, and then deflection, and of course at the very end, near the very end, we have the detection occurring in here. So for infrared spectrophotometer, okay, it is a lot more simple, okay, and this machine or this equipment, it will send out infrared lights of different frequency into our sample. But first, we will use a mirror to split off these sets of infrared lights of many different frequency. So let me just draw a beam of light in here. So this beam of light contains infrared light of many different frequencies. So for example, it contains infrared of this frequency, pretty high you see, and then here another infrared beam of lower frequency, and yet another infrared beam with a much lower frequency. So we use a mirror to split off these infrared light into two coherent sources of infrared light, and we will pass them through. So you see I'm placing two mirrors here. So the light would then be passing through two samples. So one sample, okay, on top has your sample molecule that you want to study together with the solvent. So you have to dissolve the molecule in some kind of solvent. You can't just put the molecule in a test tube. Okay, most of the time you need to dissolve it in a solvent. And in another container, you have just the solvent alone. So solvent alone. You will see why we need to do this, okay, shortly. And then, okay, these lights, okay, the infrared light that passes through these two test tubes, they are then analyzed. Okay, so we will pass them through a mirror again. Using a mirror, we direct those lights onto like a machine, okay, which would then analyze and compare the signals, and then it will give us what we call the IR spectrum. So just like in mass spectrometry, we get the mass spectrum. In IR spectroscopy, we get an IR spectrum. So this will produce the IR spectrum. And after detection, the mass spectrometer will produce a mass spectrum. So a quick review from last time as well is that in mass spectrum, the y-axis shows abundance, and x-axis shows mass to charge ratio. Okay, so we'll get a number of signals, okay, in the mass spectrum, and the signal with the highest mass to charge ratio, it usually represents the molecular ion peak. Okay, so this is the molecular ion peak, which is the mass to charge ratio of the molecular ion, the ion you get straight from the ionization stage. Okay, so molecular ion, and all these peaks on the left, yeah, we will call these the fragment peaks. They are due to fragment ions that are formed by the fragmentation of the molecular ion. Okay, so formed by the fragmentation of the molecular ion. So below is a very quick look of what that means. So if you are studying the molecule ethanol, so C2H5OH, this will be what we call the molecule. After going through the vaporization and the ionization stage, it will be turned into the molecular ion. So vaporization plus ionization. Vaporization means turning it into gas. Ionization means turning it into a positively charged ion. So at this point, we will have C2H5OH plus. Yeah, so this could, for example, be this molecular ion, and it will produce that molecular ion peak. But that's not the end of the story. The molecular ion can further undergo fragmentation. So you see in here, it will break up into many pieces. Okay, so a fragment that you can possibly get from the molecular ion ethanol is, for example, a CH3 plus ion. So what if fragmentation happens here? Yeah, then you will get one part, okay, there is CH3 plus, and another part there is CH2OH plus. Okay, so these are what we call the fragment ions. So you will get CH3 plus and CH2OH, or you may get CH3 and CH2OH plus. So these are the so-called fragment ions. And you see, I only focus on the fragment ions instead of the neutral fragments, because the neutral fragments, they will not be detected. So fragment ions, they are detected, and the other neutral fragments, they are not detected, as they will not be deflected. Okay, so remember, deflection means they change their trajectory, they change their direction of movement, so we call this deflection. So deflection will only happen to charged ion. So if you have an like a neutral sample, so I wrote down the wrong word here, this should be neutral fragment, not neutral ion. So neutral fragments, they are not deflected, and so they are not detected. Whereas the fragment ions, they are deflected and therefore detected. Okay, so it's important that you see the difference between deflection and detection. Deflection means changing the direction of movement. So, I can move this up a little bit. So for the fragment ions, they will be deflected. So you see, this is what we call deflection. And after deflection occurs, they will hit the detector, and that's where detection occurs. But for the neutral fragments, because they will not undergo deflection at all, so they will go straight to the wall. So therefore, we say there is no deflection, and therefore there will be no detection. as they could never get to the detector, which is at this position. Okay, so this is what happens here, and this is what happens there. Okay, so that's infrared, that's mass spectrometry. Okay, so we'll now turn to another technique here, infrared spectroscopy. So we'll look at what it can do, okay, just like we learned what mass spectrometer can do. So infrared spectroscopy can help us find the type of bonds present. Okay, it cannot help us find the entire structure of the molecule, but it can still help us determine if a certain type of bond is present. So help us find the type of bond or bonds present. Okay, so type of bond present. For example, ethanol. So you see ethanol has many different types of bonds, like CH bonds, CC bonds, CO bonds, OH bonds. Okay, so when we use mass spectrometer, we can just tell what kind of fragments they are inside the molecule, and then what kind of functional groups they are in the molecule. We'll have to deduce it ourselves. But with infrared spectroscopy, we can tell if a certain type of bond is present, okay, or if it's just absent in the molecule. So that's what we mean by type of bonds present. So for example, ethanol C2H5OH has CC bonds, CH bonds, OH bonds present. So this can be revealed, okay, this information can be revealed by infrared spectroscopy. So what does the IR spectrum look like? So you see, this is what the mass spectrum looks like. It has two axes. And just like the mass spectrum, the IR spectrum also has two axes. But then there's something rather strange with the IR spectrum, okay, and it is that the y-axis shows percent transmittance. So percent transmittance means how much light, okay, has passed through. Okay, I'll explain that in a second, but let me also complete the x-axis label here first. So the x-axis label is what we call wave number. So it is measured in the unit cm-1, okay, cm to the power -1. You can think of it as like, it means something similar to frequency. So it has a similar meaning to frequency of infrared light. Okay, so more on that in a second. And unlike the mass spectrum, peaks are what we call these sticks that sticks out from the x-axis. Okay, you see they point out from the x-axis. Okay, so these are called peaks. Okay, but in IR spectrum, the peaks are actually the troughs, okay, on the diagram here, because the percent transmittance, when there are no signals, okay, it will actually be at 100% transmittance. When there is a signal, there will be dips, okay, in the graphs in here. So therefore, before I tell you anything about what peaks mean in IR spectrum, you may think that these are peaks because they kind of stand out. But now that I tell you that the baseline for percent transmittance is actually here, then you will know that, well, it is the dips. They are actually the peaks. So these are the peaks, we say. Okay, it's rather the troughs, okay, that we call peaks. Okay, kind of strange. So I'll put this in here. So this is the first unusual thing I need you to know about IR spectra, is that peaks in IR spectra are really the troughs in this graph. Okay, so they are really the troughs in the graph. And another unusual feature about the IR spectra is that with the mass spectrum, the mass to charge ratio, it will increase from left to right. So for example, if this is 58, this could mean things like 15 and 29, 43. So you see the numbers increases, in ascending order from left to right. But with IR spectra, the numbers increases in the other direction, okay? And we have actually a cutoff value that is worth mentioning. It's 1500 cm-1. So this region below 1500 cm-1, okay, I said below because the numbers actually increases from right to left, as opposed to how numbers appear on the mass spectrum, where it increases from left to right. Here, the numbers increases from right to left. So you may have like 1700 here, 3500 here, something like that. okay? So this region with wave number smaller than 1500 cm-1, we call it the fingerprint region. But before we dig any deeper, we should first look at the working principle of the infrared spectroscopy first, okay? And you see I have included a diagram here on the wave number, okay? So more on that in a second. So first, let's dig into the working principle of infrared spectroscopy. So it's actually rather simple, okay? We first look at the bonds, okay? So you see in molecules are made of bonds. And these bonds, they are not really static, okay? So molecules are made of atoms, non-metal atoms of course, okay, are connected by bonds, okay? So covalent bonds. So these covalent bonds, they are not static, okay? The covalent bonds, they are really like spring, okay? So these are really like spring. So when you look at the molecule like H2O, yeah, this is how we draw H2O, the structural formula of course, but we can sort of look at H2O as something like this, okay? So you have O at the center, and then there are two H's. Think of these as like some spherical objects, okay? So they are connected by springs, okay? So that the atoms, they bounce like a back and forth, okay, closer to and further from each other constantly all the time. So the bonds like vibrating, we say. So these things are bonds, and bonds can be likened to, you know, springs. And just like in when you work with springs, you see they bounce back and forth. We can actually do something to make the vibration more intense, and that's by supplying these bonds with a particular infrared light. So let me put down some numbers here. So this is point 1 you need to know. Point 2 is that each bond vibrates at a certain frequency. So vibrates at a certain frequency. So some vibrates at higher frequency, some vibrates at a lower frequency. The general rule here is that stronger bonds vibrate at higher frequency. So stronger bonds vibrate at higher frequency, and weaker bonds vibrate in turn at lower frequency, okay? But you really don't have to know exactly like which frequency which each bond vibrate, as the table will be given to you when questions are set on this. So each bond vibrates at a certain frequency. So when let's say we know that the OH bond, it vibrates at a certain frequency. So if we supply these bonds with a particular infrared light with the right amount of energy, so this is the third point. So if an infrared light, so this yellow thing here, this wavy line represents infrared light, has energy exactly equal to the energy of the bond, yeah, so this bond, and it becomes absorbed by the bond, the molecule will vibrate even more intensely, okay? So let's say at the beginning, the molecule is just vibrating very, very lightly, like that, before the infrared light gets inside. After it becomes absorbed, okay, after the infrared light become absorbed, so IR absorbed, the bond will vibrate intensely, okay, very vigorously, okay? So you have light vibration before, and now you have stronger vibration. And the end result is that these infrared light will then be absorbed, and then they will disappear, okay, from the sample, okay? So by looking for these missing infrared light at a particular wave number, we can tell that those bonds are present, okay? So if this is still unclear, don't worry, we have this table below. Yeah, imagine that I have say 3 different infrared lights, okay, that I'm shining onto a molecule. So let's just say I have 3 different types of infrared light. Let me use colors to help. So this is the OH bond, okay, infrared light, and then we have the like C, okay, like maybe C double bond infrared light, and then we have also the like a CO double bond infrared light. So when we shine, okay, these three infrared lights, so let me compare these two. You see these three infrared lights, notice that they have increasing wave number. Yeah, meaning they have higher and higher frequency. Okay, so look at these numbers. The smaller the number, or the smaller the wave number, the lower the frequency. So this is why I draw this infrared light with different, frequency. Okay, this one looks the most intense, the least intense, the red one, and this one below looks the most intense. So when we shine these onto molecules like these, so we have, let's just say this is a sample with just CH bonds. So the simplest example I can think of is methane. Okay, so look at methane. Methane, it has only CH bonds. So when I shine these three infrared light onto this sample of methane, so because the blue wavy line represents infrared light that has energy equals that of an OH bond. The red wavy line here represents infrared light that has energy equals to that of a CO double bond, and the red one has energy equals to that of a C double bond, and that these three bonds are absent. Okay, so notice that CC double bond, CO double bond, OH single bond, they are all absent. So that means none of these bonds, none of these infrared light will be absorbed. So when they go in at the same time, they will also come out at the same time. Okay, none of it will be absorbed. So therefore, at these different parts of the infrared spectrum, so pay attention to these numbers now. So 16 and 10, 1680 and 3230. So let me draw the infrared spectrum in here. So we will look at these three particular regions. So we have 1610, yeah, approximately will do. And then 1680, and then we have 3230. So these corresponds to these three bonds. Okay, so the blue one, the yellow one, and then the red one. So you see, for this particular example, methane, the percent transmittance should be 100% for all these bonds. That's because none of these bonds are present, and therefore none of these infrared light will be absorbed. And as a result of that, the graph should look like this. Okay, so you have nothing absorbed in those points. Yeah, and let's not worry about the fingerprint region for now. So if this example still doesn't make sense to you, don't worry, we have another one. What about another molecule? Okay, let's say now I have ethanol. So CH3CH2OH. So note that ethanol has OH bond, which is the one of the bonds we are interested in finding. Okay, so we have CC double bond. So we have CC double bond absent on the left. Yeah, and in here we have no C double bond still, no CO double bond still, but we have OH single bond. And as a result of that, we'll see a dip, or rather I should say a peak at this region. And there should continue to be no dip, okay, at the yellow and the red region. So what do we say here? For the first molecule, CH4, we say there are no peaks because there are no dips at any of these positions, 1, 2, 3. And in the second molecule, ethanol, so you see this is methane, this is ethanol. In ethanol, there's one peak, and that peak is over here. Okay, this is because of the OH bond, okay, present. Yeah, and of course with molecules with more than one of the functional groups, okay, like ethanoic acid, yeah, or maybe like ketone, okay, yeah, they may have other peaks instead. Okay, so for example, if we have like propanol, okay, like C double bond OC, yeah, then this molecule here, as you may have guessed, yeah, it will have CO double bond instead of the other two bonds. So then we will have like another peak. So we will not have CC double bond this time, but we do have a CO double bond, and we have no OH bond this time. So for this example, then we will have a like a dip in this position instead. Okay, yeah, but I'm not going to draw it out, so you get the idea. So knowing this is very important. Yeah, so knowing how to interpret the IR spectrum is important, because you see in here, the CO double bond will be missing because it becomes absorbed. Okay, yeah, so this signal, oh, actually it should be the other one, my bad. So it should be the blue one that is absorbed. So if you're wondering why did I not include the blue wavy line here, that's because when an OH bond is present, yeah, when the OH bond is present, infrared light with energy, okay, corresponding to the OH bond will become absorbed by the molecule. Note that the molecule is inside the test tube. So if it absorbs the blue infrared light, it will be missing, okay, in what comes out. So therefore, you can say that these are the infrared light that goes into the molecule, into the sample, and these are the infrared light that comes out. So when we compare what goes in and what comes out, we can tell which bond is present in our sample. So note that the sample is placed in the test tube. Okay, and then there's infrared light going in, and then there's infrared light going out. So by comparing what goes in and what comes out, we can find out which wave number, okay, is missing, and therefore which bond is present. So let me summarize it on the right. So when OH bond is present, then infrared light with energy corresponding to the OH bond will be absorbed. And when it becomes absorbed, it will not be transmitted. Okay, so you see these are the transmitted light. Transmitted means it passes through the sample. So this is why the percent transmittance are 100% for the yellow and the red one. Yeah, because they are still there in what comes out. That means they were not absorbed. And why were they not absorbed? That's because there were no bonds present in the molecules. There are CC double bonds and CO double bond. They are not present. If they are not present, those infrared lights will not be absorbed. And if they're not absorbed, the percent transmittance should be 100%. Okay, at these 2 points. Okay, 100%. So let me put on the third point here. So infrared light with energy corresponding to that of an OH bond will be absorbed, okay, and the percent transmittance of the OH bond will fall below 100%, producing a peak. So this is what you see here. It will fall below 100%. This is where 100% is. Okay, it will fall below that. So that produces a peak. So producing a peak, which looks more like a depression on the graph. So that's the working principle of infrared spectroscopy. So it may look like to you that this technique doesn't have much use, okay, but actually it's quite useful, okay. Oh, and before I forget, let me talk about the 1500 cm minus 1, okay. The region below, below the 1500 cm minus 1, we call it the fingerprint region. So just like everyone has a unique fingerprint, you see the fingerprint region is unique to a given molecule. And because we have this problem, so let's think about this problem together. We have ethanol, and then we have propanol. So when you look at the types of bonds present in this molecule, right, let me draw an additional CH2 group in the middle to indicate that this is propanol, or propan-1-ol, I should say. So this one on the left is ethanol. This one on the right is propan-1-ol. Yeah, if you look closely, you will see that it has the same set of bonds, okay? They both have CH bonds, apparently. Yeah, so you see many CH bonds at many different locations on these two molecules. You see a CC bond. Yeah, you see many CC bonds as well. You see CO single bonds. You also see OH single bonds. So at first glance, it may occur to you that, or it may appear to you that these two molecules will have the exact same IR spectrum. because they have the exact same types of bonds. Okay, so and let me put down the title here. So what's so special about the fingerprint region? You won't be asked to analyze the fingerprint region, but I need you to know that, well, there's something we can use to tell apart two molecules, even if they have the exact same type of bonds. So remember, the fingerprint region is the region with wave number smaller than 1500, say Cn-1. So that's the, oops, just a moment. The fingerprint region has a wave number lower than 1500 Cn-1. Note that both molecules, so ethanol and propan-1O, have the exact same type of bonds. Okay, so I have the exact same, notice the word type, okay, so types of bonds, and they are CC, CH, CO, and OH. Okay, so you have CH, CC, CO, single bond, and then you have the OH. Okay, so 4 types of bonds. Okay, does that mean they will have the exact same IR spectrum? Well, no. Okay, so they would not have an identical IR spectrum or spectra. Yeah, at least not at the region lower than 1500 Cn-1. That's because the region below 1500 Cn-1 is what we call the fingerprint region. So you see this part, this is fingerprint region. It is produced by the complex vibration of the entire molecule. So you see, we mentioned earlier that bonds vibrate. That's true, okay? But don't forget that the entire molecule can also vibrate, okay? Just like if you imagine that there to be like many different spheres, they are connected by like a spring system. So if you vibrate one bond, well, most of the time you don't just vibrate this end of the system, you're vibrating the entire thing, okay? So when the bond vibrates, the molecule might also vibrate like together with it. And this is what we look at in the fingerprint region. So you won't be asked to analyze it, but you do have to know that the fingerprint region is due to the complex vibration of molecule. So while they both have OH bonds, yeah, I can tell you that this has a wave number that corresponds to 3250 Cn-1 roughly, and CH corresponds to roughly 3000 Cn-1. So does that mean that they will have the exact same, infrared spectra? Well, not necessarily, okay, so not necessarily. So when you look at this diagram in here, and yeah, you may find that they both have peaks at these two regions, okay, but then the pattern, okay, you observe in the region smaller than 1500, okay, so lower than 1500 Cn-1, this the fingerprint region, is very different for the two molecules. So what is the takeaway here? Okay, it is that the two molecules, if they have the exact same type of bonds, they may have a very similar pattern, okay, above 1500 Cn-1. So note the word above. So above 1500 Cn-1, two molecules with the exact same type of bonds will have a similar pattern in this region. So two molecules with the exact same type of bonds, so exact same type or types of bonds, yeah, will have a similar, if not identical, pattern. So if not identical pattern in this region being above 1500 Cn-1, just this part, okay, just this part. In this region, however, below 1500 Cn-1, the two molecules, no matter how many similarities you think they share, okay, like you see these two, they look similar enough, right? Even the type of bonds, they're exactly identical. Yeah, but then because the molecule are actually different, okay, so one is ethanol, one is propanol, they have different size, okay, they're different molecules, okay. The two molecules, no matter how similar they are, as long as they are not the same molecule, okay, so no matter how similar they are, as long as they are two different molecules, like ethanol and propane 2O, propane 1O, so as long as they are two different molecules, the fingerprint region in red will be different. It must be different because it's due to the complex vibration of the entire molecule, and that's unique to the molecule, to each individual molecule. Just like your fingerprint is unique to you, my fingerprint is unique to me. So the fingerprint region must always be different. So that's what you should know about the fingerprint region. So then the other use of IR spectroscopy that I can think of is to follow the progress of reaction. So this is a very, actually the last important use of infrared spectroscopy that I want to discuss with you, or is the use of IR spectroscopy. Okay, and to me the most important use is number one, to follow the progress of a reaction without touching, okay, what is inside the reaction mixture, making this a rather non-intrusive technique. You don't have to really touch or react with the molecule inside the sample. Remember, on the previous page, we are just shining lights. Yeah, these lights are infrared light. When you shine light on a sample, I think we both agree that we are not changing or chemically modifying what is inside the solution. And I almost forget. Why do we have to use a mirror? Okay, so this is like a mirror, or like some kind of device that will help split light, okay, into two identical stream of light. Why do we have to pass light into these two samples? One has sample and the solvent, the other has a solvent alone, because we don't want to look at the signals due to the solvent. After all, we are analyzing our sample, but no matter how much we like, okay, we cannot just have the sample inside the test tube. We must dissolve it in some kind of solvent. But then the downside of doing this is that when we use infrared spectroscopy, this method we described, to analyze just the sample alone, let's just forget about this solvent, okay, for the moment. If we use infrared spectroscopy to analyze this test tube, okay, and its content, we are not just looking at the bonds due to just the sample molecule. We also have some bonds, okay, in the solvent molecule. So if you don't do anything, okay, about this, then you wouldn't know whether the IR spectrum that you get is reflecting the type of bonds present in the sample molecule or the type of bonds present in the solvent. So that means you're confusing yourself. You don't know whether the bonds you find in the spectrum is actually due to the sample or due to your solvent. So to solve this problem, okay, the group of scientists who invented this technique, they have some like a solution, okay, some workaround, is to first use the mirror to split the infrared light into two identical beams, and then we pass these identical infrared light into two test tubes. One has sample and the solvent, the other has solvent only. Yeah, by comparing these two, comparing the results from these two test tubes, we can just subtract those bonds due to the solvent alone. So it's kind of like in here, let's say, let's call samples molecule A, and let's call solvent B, okay, and here we have B alone. Yeah, if you know, like, let's say A and B are two different person, okay, together they have $10, okay, but you wouldn't know like who has how much money, okay, so but you do know that A and B together they have $10. So to find out how much money each person has, well, you will maybe first isolate B out, okay, isolate person B out, and then find out how much money he has got, and then you can then subtract this from the total amount of money. Then you will know how much money is actually due to A alone. Yeah, so this very genius technique, okay, can be used to identify the type of bonds present in just the sample molecule, but not from the solvent. So that's something you should know. So when we use infrared spectroscopy, back to where we were, okay, we can follow the progress of a reaction. Yeah, an example reaction that you have learned in organic chemistry chapter is the oxidation of primary alcohol by oxidizing agent like K2Cl2O7 acidified. And I will take ethanol as an example. So you have ethanol in here with OH, CH3, H, and H. So when we first oxidize it, yeah, it will be turned into ethanol. So make sure you stop the video to work it out yourself. Okay, remember we said oxidation here is the removal of hydrogen. Yeah, so oxidation is the removal of not any two random hydrogen, but of these two hydrogen. You see one from here, one from here, so we move these two hydrogens. Then we need to turn this CO single bond into CO double bond. Yeah, because carbon must form like 4 bonds at the same time. Okay, so yeah, sorry, I just made a mistake here. There shouldn't be any H at this position. Okay, so I took it away. So this is ethanol. So we have ethanol as the reactant. We have ethanol in here. Yeah, and when we carry on with the oxidation reaction, we will be at another molecule, ethanoic acid. Okay, here we are using another definition of oxidation, that being the gain of oxygen. So the gain of oxygen. So where did that oxygen go? We stick it between the CO and between the C and H. It's just as if we took out a saw. Okay, we cut off the C and H at the middle, and we insert the O between them. Okay, so we insert an O in between the C and H. So that's how you get the ethanoic acid on the right. So now we can look at the molecules in here and see what kind of bonds they have. Okay, then you will understand what I mean by to follow the progress of a reaction. Okay, so let me cut this out and move it over to the right hand side first. So when you look at the type of bonds present, yeah, we will look at just 3 types of bonds. Okay, so OH bonds, maybe we have OH bonds. We will look at CO double bonds, and then we'll look at like a CH single bonds maybe. Okay, but we tend not to look at these last 2 bonds because they are almost always present in all kinds of organic molecules. So we usually will look for like some less usual bonds, okay, like OH bonds and CO double bond when we say we are monitoring the progress of reaction. So first of all, when we look at OH bonds, yeah, you should see that this molecule has OH bond. Yeah, this is where the OH bond is at. Yeah, the molecule in the middle, however, it will no longer have OH bond, but in exchange, it gets a CO double bond. And finally, when it gets to the ethanoic acid stage, it will have both the OH and the CO double bond. Yeah, so you see, the middle molecule has CO double bond but no OH. The first molecule has OH but no CO double bond. Yeah, but the other bonds, they are always present. Yeah, so this is why I said these bonds, they are of less importance. Yeah, because these bonds are almost always present. So these bonds are almost always present in organic molecules. Of course, you can give some counter example like tetrachloromethane, CCl4. CCl4, of course, will not have CC bond or CH bond, but for most organic molecules, they will have both of these bonds. So this is why we tend not to look at these, bonds. Okay, we only look at the OH or maybe CO double bond. And as you can see here, when let me just number this as A. Let me just make it A, make this B, and make this C. If we are to analyze the IR spectra of these 3 molecules, okay, what do we have? So let me just label the OH bond first. So this is where the OH bond should be at, the absorption peak. The CO double bond should be around here, so at around 1600 or 1700 cm-1, say approximately would do. Yeah, and then you have OH here, which has a rather broad peak at about 3,500 cm minus 1. Yeah, and yeah, like we will look at just these two at the moment. So we have 1, 2, and 3. Yeah, so this corresponds to the first molecule, the second molecule, and the third molecule. You see signals come and go as we carry out the oxidation. Okay, so first we will have the OH peak, but there should not be any CO peak at the very beginning. Yeah, we are ignoring the fingerprint region for now. Okay, so let's just forget about the fingerprint region like for the moment, as you will not be analyzing it anyway. So in the middle molecule, ethanol, we will not have OH peak anymore. But then suddenly we will have a very sharp CO bond, CO double bond peak. Okay, and finally when the oxidation is complete, okay, meaning ethanol is turned fully into ethanol acid, then both the OH peak and the CO peak, they can be observed. So therefore, when you carry out the reflux reaction, okay, so remember that we can use reflux to completely oxidize ethanol into ethanol acid. Okay, so ethanol plus ethanol, remember, is a primary alcohol. So when you mix it with oxidizing agents like potassium dichromate, and then you use the reflux setup here. So this is the reflux setup where water comes in from below and water leaves from above. So H2O in and H2O out from above. You will see that ethanol, it will slowly turn from, the primary alcohol stage to the, or I should say through the ethanol. Yeah, so through the ethanol stage and finally to the ethanoic acid stage. Yeah, and this method called infrared spectroscopy allows a non-intrusive way to monitor how far did the oxidation reaction go. Did it just stop at ethanol, or did it go all the way to ethanoic acid? It provides you with a non-invasive way. So to do this, you just have to draw sample from time to time from this reaction mixture. Maybe at the very beginning, when the reaction just started, okay, there will just be ethanol. Okay, so when you take out a small sample and then study it using infrared spectroscopy, remember you're just shining lights into your sample, you'll find just this graph. Okay, but then let's say 30 minutes, okay, after you started the oxidation reaction, yeah, you expect that, oh, maybe most of the ethanol have been converted to ethanol. Well, then you take out the sample again from the reaction mixture 30 minutes after the oxidation has started. You will have noticed that, oh, the OH peak is gone, and in exchange you get the CO double bond peak. That way now most of the content, most of the chemical inside the flask should be ethanol. And if you wait for, let's say, 4 hours, you're unsure whether you should stop the oxidation. Well, after 4 hours, you take a sample again, you check if there's ethanoic acid in there. So how we do that? We study the infrared spectrum again. If you see both the OH and the CO double bond peak, that means oxidation is complete, as only ethanoic acid can have both the CO double bond and the OH bond. So this is an incredibly useful, okay, application of infrared spectroscopy, the first one, okay, that I want to discuss with you. The second one, it's also quite useful, you can say, is in the breathalyzer, okay, is to analyze analyze if ethanol is present in the breath of a drunk driver. Yeah, to check if somebody is drunk driving, that is, okay. So in the breath of a drunk driver. In the redox chapter, you have learned a alternative technique. So that alternative technique, we call it the breathalyzer, okay. So the alternative technique to this method is to use breathalyzer. So breathalyzer comes from you joining two words, breath and analyzer, okay. So breathalyzer, in this device, there is a column of potassium dichromate crystal, okay, which is of course orange in color, So K2Cl2O7 crystal. And to use this device, okay, so there is a tube, okay, that you can blow into. So let's say this driver is really drunk, okay. So in his breath, there should be, you know, quite some ethanol, okay. So there's like a bit of ethanol, okay, because if you are drunk, okay, ethanol will not just stay in your blood, it will be exhaled into your breath, okay. So there is ethanol in drunk driver's breath. So what happens to the ethanol? The ethanol will be blown out or exhaled out from this driver, and it will react with potassium dichromate in a redox reaction that you have learned in, of course, the redox chapter. So Cl2O7 2 minus, the ion, the active ion present in potassium dichromate. So this is from K2Cl2O7. It will react with ethanol, which is C2H5OH. Yeah, and then a redox reaction will happen. So you know redox. Redox means something is oxidized and something is reduced at the same time. So we have ethanoic acid formed from ethanol. So this we call oxidation, of course. Okay, so we have oxidation. At the same time, something will be reduced. Okay, so we have red or reduction in here. So in which the dichromate ion will be reduced to chromium-3, which you know is a green substance. Okay, so dichromate starts off as an orange substance, but chromium-3 in a different oxidation state than dichromate. Note that dichromate has oxidation state equals +6. Chromium-3 has oxidation state equal +3. So this is green in color. So you will notice a color change from orange to green. So that's the color change. And if you are the officer, who is testing this drunk driver to see if he's drunk, okay, you're passing his breath into this column of potassium dichromate crystal, you will notice some greening in the crystals. Okay, so at least part of it will turn green, because this now becomes chromium-3, and there are of course some remaining dichromate here. So the more drunk he is, okay, you know, the more green, okay, it will become. Okay, so let's say this is more green now. So more greening means there's more ethanol. Okay, so this is more ethanol. Because the more ethanol there are, the more dichromate will be reduced. Okay, and so the more green, okay, the column will become. And if there's less ethanol, this is what will happen. So this is the redox technique, okay, of determining if like a driver is drunk driving. So what about back to this chapter? Okay, I said like this is the second application, okay, of infrared spectroscopy, right? So we will look at the structure of ethanol again. You can see some bonds, okay, that are unique to ethanol, like maybe CC bonds, like CH bonds, okay, and like maybe CO bonds, and then maybe OH bond. But which of these bonds should we look for, okay, if we are to study if a drunk driver has ethanol in his breath? Well, a lot of students would say maybe it's OH bond because ethanol, you know, the functional group is an OH group. But then using OH group as a way to identify if ethanol is present is a very bad idea, because you see in a person's breath, okay, whether or not you're drunk, there will be water vapor. Okay, so let me just draw like two guys in here. So there's like this guy who is actually not drunk, okay, so not drunk, and then there's a guy here who is pretty drunk. So in his or her breath, okay, there will be ethanol and of course H2O. So if you're looking for H2O, it will make you look kind of silly, because OH bond is always there, okay, whether or not you are drunk. So even for like a person who are not drunk, there will at least be some H2O in his or her breath. So therefore we shouldn't be looking for OH bond. Instead, we should be looking for bonds that are unique to these organic compounds, okay, like maybe CC or maybe CO, okay, yeah, but certainly not OH bond, okay, yeah. So the conclusion here is, so you see this is the structure of ethanol. So ethanol has various bonds, but to check if a drunk driver, to check if a driver is drunk driving, so it's drunk driving, is wise, okay, drunk driving, it's wise to be looking for CC bonds or CH bonds or CO bonds rather than OH bonds, okay? So we should be looking for like a CH or CC or CO, and we should not be looking for OH bonds. Okay, so we should not be looking for OH bonds, as well this may not seem obvious, okay, as even H2O, a normal component of breath, has OH bond. So don't do this, okay, don't look for OH bonds, look for the other bonds, okay, using the same technique we learned on the previous page, okay. So a normal component of breath, of course there's water vapor in our breath. So that concludes the first and second applications of infrared spectroscopy.